in less cooling, essentially, or otherwise more heating or an increase in temperature. And of course, water vapor is another fact of that. Water vapor has the largest effect on trapping heat energy, so it's the most potent greenhouse gas. But oftentimes it's not listed because it varies so much in concentration and is constantly condensing into liquid water, ice, and snow, at which point it exits the atmosphere and therefore doesn't contribute to the overall greenhouse effect. Scientists estimate that 36 to 66% of the greenhouse effect is due to water vapor. The IPCC estimates that that's around 50%. So even though we often talk about CO2 and methane and other kinds of greenhouse gases, water vapor is another really critical component of Earth's atmosphere that contributes to an overall warming effect. And you can see this here with relative sort of contributions to all of that, with carbon dioxide and methane, the two most commonly thought of greenhouse gases, as well as some others. And you also see here the present concentrations compared to pre-industrial concentrations, all of which are higher. And that's particularly acute for carbon dioxide and methane, which is why those two are often associated with the greenhouse or the greenhouse effect most directly. So radiative forcing is the change in the balance between radiation coming into the atmosphere and radiation going out of the atmosphere. If it's positive, then Earth is warming up, and if it's negative, then the Earth is cooling. Solar irradiance accounts for the increased energy coming from the sun, and solar radiative forcing has been measured since 1850. And you can see here in the graph, again, sort of the overall effect of different atmospheric components, substances such as the greenhouse gases, but also ozone and water vapor and so forth. And there's these collectively influence the overall ability of our atmosphere to warm the Earth's surface, and they have a differential impacts on that overall ability. However, the key sort of takeaway message here is that the more of this there is in the atmosphere, the greater that warming effect is going to be. So oftentimes when we talk about climate change, people are quick to point out that the Earth's climate has always changed, and this is in fact true. Earth's climate has not remained constant throughout its history. There have been periods when the Earth was warmer and periods when the Earth was cooler. The key difference, however, is that these periods have been due to non-human events, non-human activities. And the thing that makes our current period so much different is simply the sheer size of impact that human activities are having on the Earth's climate system. Two key ways that we think about Earth's climate are the two greatest variables or markers of the climate system, temperature and precipitation. And we can't measure precipitation in the distant past, but we can measure temperature both directly and indirectly, as well as the composition of the atmosphere at particular points in Earth's history. And these come from sediments, fossilized animal shells, other sources. And while these clearly are not as direct as the measurements that we're able to take today on a very a very focused timeline, they do provide some evidence into Earth's history and how climate has varied over time. But one thing we do know from those measurements is that there is a historic correlation between Earth's overall average surface temperature and carbon dioxide levels in the atmosphere. So one way, or one example through which these historical trends are measured is through bubbles of ancient atmosphere trapped in ice. So laboratory analysis of geologic sediments and other layered materials help us do this and provide a mechanism by taking these ice cores to look far into the distant past of Earth's history and see what the Earth's climate system looked like at those times. Now